we'll be walking through Apache Spark. Apache Spark is a distributed big data processing framework which is very similar to Hadoop. It is in many ways built on top of Hadoop, but it extends the functionality of Hadoop and offers a lot more algorithms and faster data processing and covers a broader base of applications compared to Hadoop. So this will be the outline of our session today. We'll be having a brief introduction about what is Spark, what are the design goals of Spark, what was the reason Spark was built in the first place, how it improves over Hadoop, and we briefly compare Spark with Hadoop because both of them offer similar functionalities. And then Spark has got quite a few components which specialize in different applications and different levels. So we'll be taking a look at each of these components and I'll be briefing over them. And finally, we discuss certain use cases of Spark. Spark being a very young project, it is just being adopted by the community, but it definitely is the future of big data and large-scale computing. So I have selected very few use cases of Spark which are actually used in industry. They're increasing by the day. So that's the agenda of this session. Spark was developed by reflecting Hadoop only. It was developed at the University of Berkeley. One main thing which Spark does compared to Hadoop is it does more of in-memory data processing as compared to doing a disk-based processing. In the sense that if you take MapReduce paradigm in Hadoop, it consists of a lot of mappers and reducers. Each mapper processes a set of data and then transfers that intermediate data to the disk. Disk, as you know, is a lot slower than in-memory data. So what Spark does as an improvement over Hadoop is most of the data which it processes in an intermediate state is stored in memory as compared to disk. The complications of storing data in memory and having it in a distributed platform is actually mitigated by the Spark architecture, which we'll be seeing in the upcoming slides. So that is a major difference between Spark and Hadoop. Spark extends the MapReduce model. It does not do any drastic change to the MapReduce computation in general. It extends the MapReduce model to support more types of computations. If you're familiar with MapReduce, you must be knowing how non-trivial it is to write a simple word count program. So that is because of the way MapReduce is structured. The abstraction model in MapReduce is a lot more less sophisticated compared to Spark. So what Spark does is it exactly addresses this problem so that we can think in terms of the problem space rather than converting a problem into a MapReduce. For example, let us say that you are doing a filter operation in Hadoop. What you would go about doing is you will split it into a map phase and a reduce phase, and then you'll figure out what to do in the map phase. There are a lot of algorithms wherein you don't do a lot in the map space except mapping a key value. Like if you take the filter example again, you won't do any sort of computing in the map phase except sorting the keys. You'll only do the filtering in the reduce phase. So that is a very poor abstraction if you're writing algorithm in Hadoop. So what Spark does is it abstracts the mapper and the reducer so that you can write your filter or word count or aggregation without thinking in terms of MapReduce. So that is one difference with Spark. The other thing is, like I told, if you want to write a sorting algorithm, sorting is an example of an iterative algorithm, wherein you have to think in terms of map and reduce, which you need not do for Spark. Most of the big data, if you see in the real world, is organized in terms of graphs. Your list of friends and their friends is an example of a graph which is used in Facebook. And if you do a Google for something, you get a lot of pages, and then these pages are ranked according to their relevancy. This is another example of graph processing. So most big data in the world is organized in terms of graphs naturally. So if we are processing with big data, we need a framework which is optimized for graphs processing. So Spark is exactly that. Spark addresses graph processing in a very optimized way. It's got a separate component for processing graphs, which we'll be looking at shortly, and it's got a lot of algorithms built in for doing common graph processing tasks also. So that is one more thing with Spark. You can directly write SQL statements in Spark. Compare that with Hadoop. Hadoop initially didn't have any provision for that, but then there were a couple of projects which were built on top of Hadoop, like Impala and Hive. So what they do is they have a subset of SQL which is implemented in Hive and Impala, and that is in turn broken down, parsed, and converted into MapReduce tasks. But in Spark, you can directly write first-class SQL statements and embed it in your program. It can be in Python or Java or Scala. So that is one more major advantage with Spark. You need not learn a new data store like Hive or Impala. You can, if you're a database administrator and you want to run a Spark query, you can directly write it in SQL. So Spark is designed to be highly accessible in the sense that if you're aware of Hadoop, you must be knowing that we can only program it in Java, but Spark is more of an API and a platform rather than a framework. So you can write MapReduce and big data processing logic in Python, Java, Scala, or SQL. So it has native support for all these four programming languages. That's a big improvement compared to Hadoop. So most of the DevOps must be having the fear that we need an entirely different set of architecture for running Spark programs, which is not true at all. You can run Spark on top of existing Hadoop infrastructure like AWS, Elastic MapReduce, Cloudera platform, whatever. So Spark is designed to be backward compatible with existing Hadoop infrastructure. So you need not have the fear of changing or revamping your whole infrastructure when you're moving from Hadoop to Spark. That is one more advantage which Spark designers took into consideration while developing Spark. So that's a brief overview of Spark. So these are the major components which are involved in Spark. So like I told, there is a separate component for running Spark SQL statements. As you must be knowing, most of the data in the world is organized in SQL databases. So if you don't have any provision to do it or process it directly, then you have to learn a lot of intermediate frameworks like Hive or convert them into structured relational data and then process it using Hive. So Spark mediates all those issues, and then you can bypass and directly issue SQL statements and do big data processing. And Spark has also got a streaming interface. If you're aware of Hadoop paradigm, you must be knowing that Hadoop is best suited for batch processing tasks, but it performs poorly on streaming data. Streaming data, if you want an example, let us take that you're running an e-commerce store, and some anonymous user comes and browses your store, and he spends a lot of time in the men's section for like 10 minutes, and then based on your web analytics, you derive that insight that this user has spent like more than 15 minutes searching for a product in the men's section. So what you do is you automatically feed this data to the backend, and it generates a coupon for like 10% discount, and then forwards it to that specific user. So this is an example of a batch processing task. This is an example of streaming task where you immediately process data and give it real time. So Hadoop didn't have this provision before, but Spark addresses this problem by giving a separate interface for streaming. Spark has also got a component called mlib. Mlib is specifically a collection of algorithms which are commonly used in machine learning. As you must be learning, we do a lot of machine learning in big data processing. So Spark takes all the common algorithms, optimizes them to run on top of Spark platform, and offers you. All you have to do is call the algorithms with the appropriate data, and Spark is going to do all the hard work for you behind the scenes and then generate you the results. So this is something which is unique to Spark. If you take Hadoop, it doesn't have any built-in machine learning capabilities. You have to use a platform like Mahout. So Spark, that is not the case. Like I mentioned before, this is very, very special for Spark. You have a separate graph processing component which is used in Spark. It's called GraphX. It contains a set of graph processing algorithms. It works on par with the fastest graph systems which are available in today's industry, like Neo4j or whatever. So you can transform and join graphs efficiently using Spark. And if you have heard of Pregel, Pregel is an Apache framework which was proposed by Google. Spark works seamlessly with Pregel and comes with a lot of flexible graph algorithms like PageRank, connected components, triangle count, SVD, and all that. So GraphX is a very, very unique feature in terms of big data processing in Spark. So it, in fact, GraphX offers a better performance compared to other frameworks like GraphLog or Giraffe. Even if you have heard of Apache Giraffe, Giraffe is an exclusive graph processing framework which is built for big data processing of graphs, but Spark outperforms Giraffe in most cases. So you need not learn a separate framework also. That's one more advantage. So I gave a brief overview of all that. I'll be going through one by one now. We'll go take a look at Spark SQL. Spark lets you run structured queries on relational data, and like I said, you can embed your queries in Python, Scala, and Java. So this gives you a lot of tight integration with SQL, and you can run complex analytics using Spark SQL. And one more advantage is Spark SQL works with unified data, which is in the sense that you can have any kind of data. You can have your data in JSON, you can have your data in Amazon S3 data sets, you can have it in large XML files, you can even have it as log files which are physically stored in disks. All this data can be queried upon by using Spark SQL. The third advantage is Spark SQL is compatible with Hive. Internally, what they do is they have a plugin which maps your Hive query language to Spark SQL. So you can run Hive queries also on top of Spark SQL. You need not actually spend time and resources on migrating your Hive queries to Spark queries. Hive queries directly run on Spark without any conversion or modification. You can even run your custom user-defined functions which are written in Hive on top of Spark SQL. So that's a cool thing. So one more advantage with Spark SQL is it provides standard connectivity suites for all popular tools which are used in business intelligence like JDBC or ODBC. So Spark SQL plays nice with industry standard JDBC and ODBC connectors. So that's about Spark SQL. Like I mentioned before, Spark Streaming is actually a real-time language integrated APIs to do stream processing as opposed to batch processing, and you can do it in both Java and Scala. And one concern with most stream processing frameworks is the fault tolerance. So because we are dealing with real-time data, there is a high likelihood of your nodes crashing and you not getting the results. So Spark has got an excellent recovery mechanism which works on lost nodes so that you don't get your data results muted out. And you can combine stream processing with other components like SQL or mlib or graphics. So that's again one more cool thing with Spark streaming integration. And you can run streaming in both batch and interactive modes. I gave you an example of the interactive mode in the e-commerce site. An example of a batch processing is you can run a Spark query offline, and asynchronously derive the results and then store them in the data set and then retrieve it later. For example, Amazon book recommendations, you store the user's browsing history and you run an offline data processing task and then store it again in the user's profile, and when the user logs in next time you can show the processed result. So that's another example of batch processing. And streaming also integrates with a lot of existing standards like HDFS and Flume. If you've heard of Flume, it's a log processing framework which works on top of Hadoop. So streaming plays nice with Flume. It also plays nice with Kafka. Kafka is a distributed message queue which is used for again data processing in streaming mode. It was written by Twitter and is used extensively in a lot of other industries like LinkedIn. So Spark plays nice with Kafka also. That's about Spark streaming. Spark MLib is a collection of machine learning libraries which I mentioned. It runs 100 times faster than MapReduce. Like I mentioned before, this is possible because of the way Spark stores data. It stores it in memory, so that it's 100 times faster than your conventional MapReduce jobs. So it runs faster than Mahout considerably. It's got a lot of machine learning algorithms like k-means clustering, linear regression, logistic regression, naive-Bayes classification. So you can run all types of recommendation and classification algorithms on top of Spark MLib without you coming up with your own implementations. It also operates with NumPy. If you work with Python, you must be knowing that NumPy is a very popular framework for large-scale number connection. So Spark MLib, because it's got Python API, it plays nice with NumPy. And one more advantage is because Spark is backwards compatible, it can be deployed on top of existing Hadoop clusters, on top of standalone or EC2 clusters, so that you can run machine learning algorithms in MLib without modifying your infrastructure drastically. So that's one more advantage of Spark MLib. All this is possible because we store data in memory. So like how Hadoop operates on top of HDFS, we have RDD in Spark. RDD is nothing but resilient distributed data. It is the basic abstraction unit of Spark. It's an immutable collection of elements which can be operated in parallel. So Spark provides a first-class API to interact directly with RDDs, and RDDs have a higher partition tolerance compared to Spark. For example, in HDFS you achieve partition tolerance by doing replication, but RDD the replication factor is a lot lesser compared to HDFS, so that occupies a lot of less disk space comparatively. But in Spark it stores all the metadata for retrieving RDD when it crashes, so that the replication factor is a lot lesser. The Spark paper discusses a lot about RDD and how it is implemented. So, but as an end user, you just have to know that you can store data in RDD and it is totally immutable, and it's got a high degree of fault tolerance compared to HDFS. So that's about RDD. All the components which I detailed before, like MLib, SQL, graphics, and streaming, they make heavy usage of RDD. So that's about a tour of the components of Spark. I've got 3 case studies in Spark in different domains. One is text analytics, the other one is decision trees, the third one is recommendation engine. I'll be giving a brief overview of how it is used in all these 3. So like I mentioned before, Spark is compatible with Java, so you can use any Java API in that. So if you have an NLP framework in Java like OpenNLP or UIMA, you can directly use it in Spark. That's what IBM has done in their text analytics engine. It stores a lot of legacy data in HDFS. Like I told before, it's backward compatible. So it reads this data into Java RDD. I told you RDDs are the basic unit of Spark, and then it processes the data using Shark. Shark is the SQL component of Spark. They call it Shark. So, and then they extract it using UDDF. That's a user-defined function, and then they transform it. I'll just show the block diagram, which is this is the whole text analytics lifecycle. This is an example of using the alternating least squares algorithm for getting recommendations. So if you see this matrix, this is the data which is collected. The rows are the users, the columns are the songs. So this is the data of which user liked what songs, and then you factorize it based on this algorithm. And initially Spotify implemented this using Hadoop. I'll just show the flow in Hadoop. This is the algorithm which is written in Python. You can even get the source code here. So this is the workflow in Hadoop. Like I mentioned before, Hadoop writes all the data in the disk. So if the data is very huge, like the number of users or the number of songs matrix increases considerably large, so it suffers from a lot of I/O overhead because it's storing everything in HDFS. So it becomes a bottleneck. So what happens in Spark is you store the data. The same algorithm is implemented using Spark mlib. So there's no change in the code or the infrastructure. They just change the framework, and they do it iteratively and then store it in RDDs. This is a representation of your RDD because it stores data in memory. So it's represented as a RAM in the picture. So this is your Spark workflow, and this is your Hadoop workflow. So they have implemented the same algorithm in Spark, and they get a lot less results. So this is the code written in Spark using Scala. And they have optimized that algorithm to reduce the number of disk reads and I/O. So this is the actual Scala Spark mlib code which was written in Scala, which updates the matrix based on user recommendation, and it's a lot faster than Hadoop. If you see the code, it is typically a lot smaller than what you generally write in Hadoop. That's because of two reasons. One, they use Spark, which does all the hard work for you and provides you the algorithms. Two, it's written in Scala. Scala is generally more expressive as compared to Java. So if you're working on Spark, I would suggest you prefer Scala to write your business logic, because your code is a lot more maintainable and a lot easier to reason about. And we'll be having a lot of such hands-on exercises in the training program when we are working on Spark and Scala. That's it.